Um, Hi, everyone. I am Daniel Núñez. I am going to talk about shadow of in the star on a regular space-time. That was the topic of my master thesis, and I did it in collaboration with Juan Carlos de Goya. First of all, I want to tell you that the motivation for this work, it was because in the last years, the observations from Heaven Horizon Telescope give us a new tool to test the models that we have. And so I want to contribute to this, to the exploration of these models and to test it with the data that we obtained. So the work that I did was see the difference between different kind of observers, one static observer and one free fall observer for a regular space-time and compare it with the simple case that is the Schwarzschild solution. So I'm going to explain you for those who don't know what's a regular space-time, and then we're going to solve the heuristic equation for null for photons and for mass particles. And with that, we're going to use tetrads to see how does the size of the angular size of the shadow change with a static observer, and then for a free fall observer. And after that, I'm going to give you the conclusion and the bibliography. So, what is a regular black hole or a regular space-time? Maybe some of you know the word, but it's really simple. That it's only a space-time that doesn't have a physical singularity. That maybe you know the Schwarzschild solution on r equal to 0. We have a singularity that we cannot remove with a change of coordinate system. This kind of space-time, the regular space-time, avoid these problems with the metric. So for the case of high-order space-time, in the system, the coordinate system pi-level bootstrap, we see like this, the metric. And maybe some of you that work with Schwarzschild or the metrics in general know that this is a representation of the Schwarzschild solution, just that the mass is here a mass distribution function instead of a constant. And the mass distribution function for Hayward is here in 2. It depends on the parameter of the mass, M, and on the Hayward parameter length A, that is Q star. And you can see that if we take Q star equal to 0, we recover the Schwarzschild solution. So what we modeled was a star, spherical symmetric dark and opaque. And for this, we need to find how does the particle with mass vary in the spacetime. And to see, we need the heuristic equations. So we use the Lagrangian associated to that metric. And we also we need the constants of motion for particles with mass and for photons. Those are mass particle and massless particles. So using these tools, we can find first the time-like heuristic equation. We use again the Lagrangian. We're going to use the Lagrangian several times to obtain the heuristics. So we use that and the normalization of the forward velocity, and we write to 4. And using the conserved quantities, that is the energy and the angular momentum, we can write also to the explicit equations for the radial coordinate and the time coordinate, that is 5 and 6. And it's important to see that if we divided 5 by 6, we obtain an equation that only depends on the radius and on the energy of the particle with mass. And that I'm going to call it the time matter equations. So that is important. Remember it. As I said, we're going to use tetras to define the observers. One is going to be the static case, and we're going to use E with subindex 0 to 3. And for the free fall observer, we're going to use I don't remember how we say this symbol. But in English, we're going to say E prime or the free falling observer. But we're going to define two different cases, the static and free fall. So now that we have how does the matter particle moves, we need how does the photon moves on the spacetime. So we're going to need the light relativistic equations. And for that, we're going to use again the Lagrangian and obtain 7. This equation. And you can identify from this equation that you have a term associated to the kinetic energy, one for the energy in general, and one that we call the effective potential. So we are going to see the solution where the part of the kinetic energy vanished, and we obtain that to that radius. We call it the minimal radius for the photons to describe these orbits around the our star. So also you could do the second derivative of 7 and obtain this equation on 8. And if you want to obtain the maximum or minimum equation of make similar the energy and the effective potential, you arrive to a radius that represents the photosphere. And maybe you remember that the photosphere is going to be the smallest radius at which our photons could orbit around the objects in stable orbits. Semi-stable. Well, using that interpretation of the minimal radius, we could rewrite the equation 7 in terms of Rn and to vanish the energy and the angular momentum dependence. So we arrive to 10. And also, you could use again the Lagrangian and this equation to obtain an expression for the time of the photons in this case. How does it move in the space-time? Similar to the time matter equation that I defined earlier. So we arrive to 11. And maybe you are already a little exhausted with all these equations. So I'm going to explain you with a figure. What we are going to do is just to express the tangent vector of the velocity in terms of the components of our tetra. And what we're saying is that the angle alpha of that is the angular size of the shadow, is going to describe the half of the diameter of our object or of the circular orbits that the photons follow. So we have the expression 12 making this comparison, and using again the equation of the this equation, you could arrive at an equation in terms of the size of the shadow and the minimal radius and the coordinate radius in general. So we arrive to 13 and 14. And this is what we want. We want the angular size of the shadow in terms of the radius to describe the collapse as the star have a surface smaller and smaller. So what we're going to do first is to step on the surface of the star and see how it decreases. And what we are going to use is the time matter equation, because those are particles with mass. And where we arrive to 15, that is, as you can see, we have the radius of the star and the initial radius of the star when the radius of the star is equal to the initial radius, this integral makes 0. So the coordinate time of the star becomes 0. What we're saying here is that the collapse will start when the time of the star is equal to 0. And before I describe you the 3 stages of the collapse, I want to tell you that you could derive an equation that makes a similarity between the radius of the star, that is Rs, and the minimal radius for the photon, that is Rm. Using the angular size of the equation of the angular size of the shadow for a free fall observer. What is important is that here if you put a value for Rs, you obtain automatically the minimal radius for the photons. As I said, when the radius of the star is the initial radius, that is Rs, it's Ri, you obtain that the minimal radius of the photons also is Ri. And as the collapse continues, the radius of the star is going to decrease, and the radius of the photons also will decrease. So the collapse is divided in 3 stages. The first one is where you have a static star, and that is for the coordinate time negative. And when you arrive to the coordinate time equal to 0, we say that the collapse starts. So I don't know if you could see the colors, but here is the first stage is blue, the second stage is green, and the final stage is red. So first stage, start. Your star is not collapsing. Second stage, your star starts to collapse, and it arrives a point where your minimal radius becomes the radius of the photosphere. I don't want to enter in too much details, but the radius of the star have a value for that time, and we're going to call that Rs2. And that's when the second stage is. And then the third stage is the rest of the collapse. Here, this is like the surface of the star, obviously, as it decreases. And the first case is a static observer, so it remains in the same radius. So the first stage, as the star is static, you may say that the angular size of the shadow also it's a constant, because you're not changing like nothing. So it's easy to see that the angular size of the shadows only depends on the initial radius of the star and the position of the observer. Then it start to collapse, and the last photon that leaves the surface of the star as it starts to collapse takes a time to arrive to the observer. So you need to take that into account, and it arrives at the observer at a time T01 that is different from 0, that is the time of the star when it starts to collapse. So then at that time it starts for the observer the second stage. At the second stage, you don't have a radius of the star fixed, so you are not going to have also radius minimum for the photons fixed, and it starts to decrease until a point when it becomes the radius of the photosphere. So at that time, it finished the second stage, and you could call it again another time, label TO2, that is associated to minimal radius equal to radius of the photosphere. And for the rest of the collapse, as you could poke, the photons only describe circular orbits around the photosphere, and so the angular size of the shadows becomes again constant. And this is the value. This is the result of the collapse. On the left, we have the case of Schwarzschild, that is when the length scale parameter of Hayward is equal to 0. And on the right, we have an extremal case of Hayward. And maybe it's difficult to see it, but in the case of Hayward, we achieve angular size of the shadow smaller. And that's because as you change the metric, you also change some values of importance. That is the radius of the photosphere. As you make greater the Hayward parameter, you make smaller the radius of the photosphere. You have a radius smaller, then you have more time to the photons to arrive to that radius. So you achieve angular size of shadows smaller. And for the case of a free fall observer, the treatment is the same, but it's more difficult. The equations become ugly, but still analytical. And the important thing here is that as the observer doesn't have a fixed position, you could now vary the angular size of the shadow with respect to that position. So just to illustrate it, here we have the collapse of the star, the surface star. Here we have the static observer at a radius of 10. And the trajectory of our free-falling observer. In our work, we didn't consider the case when the observer could enter the star. So in all the time, it is out and a little far. And now you could see the difference between the Hayward case and the Schwarzschild case, because now on the third stage, we see on the Hayward case that the angular size of the shadow reaches a maximum and then start to decrease. And on these plots, they are like the previous ones, with the difference that now we're comparing with the radius of the observer, but the time it's moving from right to left as the observer is falling inside. And yeah, you can see the difference between one case and another. And to sum up, for the same observer at the same radius or at the same coordinate time, you could see a difference between the angular size of the shadows that it achieves. So you could distinguish between a regular metric or a singular metric. That is the case of Schwarzschild. Also, you could imagine that there is a relation between the collapse and the angular size of the shadow. As you make an object smaller, you imagine that you will see something smaller, but it's not always the case in Hayward. That is the case of the free fall observer, that the collapse is continuing, but the observer see like an object that is increasing and decreasing and decreasing and decreasing in the angular size. And this behavior is only in the case of the free fall observer, but we could study some other cases for free fall observer, like the one that I said that when it enters the object. So this is the bibliography, and that's all by my part.